Okay, let's try that again. So we have 6 polynomial functions listed here with 6 zeros, and we want to figure out if we can determine something based on the change of signs. So there's one change of sign here. We went from positive to negative. Okay? Then we went from negative to positive. That's another change of sign. And then from positive back to negative, that's a third change of sign. Okay? How about this one? How many changes of signs? Okay, 2 changes of signs. How about this one? Positive to negative is 1, and the negative to positive is, so 2. How about this one? How about this one? And lastly, okay. Now let's look at the zeros. How many positive real zeros do we have? How was the last one? 3. We went from positive to negative, from negative to positive, and then back to from positive to negative. The first one. Okay. How many positive real zeros do we have in the second equation? How many positive real zeros do we have in this one? How about in this one? How about in this one? What about in this one? Positive real. It's only one. This is that's a complex one. This one, 2 of them, not unique, okay, but 2 of them, and this one only has 1. Okay, so it was going well there for a moment, wasn't it? We had a good thing going. They matched up until this one. And what happened here? Those guys took away our opportunity to have a total of 3 positive reals. Okay? But notice that when we have 3 changes of signs, 3 positive reals, if there had been some complex ones in here, how many would there be instead? Complex conjugates always come in pairs, so they would take away 2 opportunities to be positive, right? And it would be the complex ones. Okay? So we could have 3 or 2 or 1, 2 or none, because the complex ones could have taken the opportunity away. Same thing here, 2 or 0, 1. Have to have 1 of them here. And 2 or 0, and 3 or 1. Okay? You have just figured out half of Decartes' Rule of Signs by looking at patterns. Decartes' Rule of Signs says that if you have a polynomial with good old polynomial a sub whatever, a sub n, x to the n, formally define it, the number of positive real zeros is either equal to the number of variations in signs of the function or less than that number by an even integer. Okay? 3 sign changes, you're going to have 3 positive reals or 1 positive real. If you had 5 sign changes, you'd have 5 positive reals, 3 positive reals, or 1 positive real. Okay? If you had 4 sign changes, you could have 2 positive reals or 4 positive reals or 0 positive reals. Always goes by 2s, thanks to those complex conjugates. Then Descartes also found out that if you want to know the negative real zeros, you plug in f of negative x and see how many variations of signs there would be. You trust him, or do we want to go back to our other example and try it? Trust him? Okay, you convinced? Okay. So what does this mean for us? Well, if we find out that there are no variations in sign change, then we're not going to have any positive real zeros, right? So we can eliminate all the positives. Or if we don't have any negative variations, any changes of signs when we plug in a negative x, then we know we're not going to have any negative zeros. So we can eliminate all negatives. Okay, so that can make our life a lot easier, especially when our constant on the side has a lot of possible factors. Okay? Or we have something other than 1 for our leading coefficient, which can add a whole other dimension when we're dealing with fractions. So let's describe the possible zeros here. Sign changes. 1, 2, 3. So we can have 3 positive or 1 positive. Now let's do the negative side of it. If I plug in f of negative x, I will have 6 times a negative x cubed minus 19 times a negative x squared plus 16 times a negative x minus 4. So what's my sign going to be here? How about here? How about here? How about here? Are we going to have any negative zeros to that particular function? How many sign changes do we have? Negative to negative to negative to negative, we have not changed signs, so there are no negative zeros. Okay. Good old Descartes. Yes. Right, so we'd have a negative 6x cubed. This guy's squared, so he's going to be positive, but positive x squared times a negative 19 is a negative 19x squared. And then our negative x times a positive 16 is going to get us a negative 16x, and then our negative 4. Does it make sense now? Yep. So I didn't write it all out, but all we're looking for then is how many times does the sign change between each fact, or each, what would they be called? Term, between each term. Okay? All right. We can also learn something from the upper and lower bounds. We have a couple rules here. Let's say if we have a polynomial with real coefficients and a positive leading coefficient, okay, this is a positive leading coefficient, so it doesn't work with negative 16x to the 5th. Okay? We take f of x and divide it by x minus c using synthetic division. If c is bigger than 0, and each number in the last row is either positive or zeros, then we've hit an upper bound. There's not going to be any numbers bigger than that are going to be zeros. Okay? So don't try anything higher. You're wasting your time. Okay? C is less than 0, and the numbers in the last row are alternating between positive and negative, and 0 can count either way. Then you're at a lower bound, and it's not going to do any good to try anything lower. The reason for that is if we had something like f of x equals, I don't know, we're going to just put some numbers in here. 4x to the 5th plus 6x squared minus 7x plus 3. Okay? When we plug a number in, if we plug a number factors of 3/4, right, or factors of 3 divided by factors of 4, let's say that we put in 1. When we plug that 1 in, and we get a number out, that number is what f of 1 is going to be. It'd be the same as plugging 1 in. 1 times 4 plus 6 times 1 minus 7 times 1 plus 3. Okay? So if we aren't changing and it just keeps getting bigger, then we're way up there and we're not going to ever turn around and come back down. Does that make sense? Okay, that was our remainder theorem. The remainder is actually f of 1. Okay? So, putting it all together, how many zeros will this have? 4. Okay, how do you know? Minus power of x is 4. 4 zeros. Okay? What are our possible zeros? How could we find values that we should even try? Factors of 4 over factors of 1, our leading coefficient. Okay. And let's see if we can eliminate any of those, but we would have plus or minus 1, plus or minus 2, and plus or minus 4. So that's 6 possibilities, which can get tedious. So now let's think about Decartes' Rule of Signs. How many sign changes? Positive, negative. 1, 2, 3, 4. So how many positive zeros can we have? 4 or 2 or 0. And those are the reals. Okay? Let's see if we can eliminate any negatives. When we plug a negative 1 in, f of negative x, sorry, not negative 1, but negative x in, negative x to the 4th, negative 2 times negative x cubed, still positive, 5 times negative x squared, still positive, negative x, or negative 8 times a negative x, that's a positive, and a positive 4. Are we going to have any negative values? We've got to cut our work down by half. Okay? So we know we don't have to try those negatives. So we're going to try 1, 2, and 4 as possible roots. Okay? And I keep saying roots, and I mean zeros, so that's what your book calls them. So I'll keep trying to remember to tell them the right thing, and you keep remembering they're the same thing. Okay? Here we go. 1, negative 2, 5, negative 1, 4. I didn't have negative 8. Didn't have to hold anybody's place. And what do you want to try first? 1. 1's the easiest number to multiply, right? We okay with skipping writing the middle thing in there? Let's just write our answer. So when we drop our 1 down, 1 times 1 is plus a negative 2. 1 times a negative 1 plus 5. 1 times 4 plus a negative 8. 1 times a negative 4 plus 0 or plus 4. Okay. So we got lucky. And notice we had an alternating sign pattern here. Had we gotten all positives here, we would say we're at an upper bound. There's no reason to try anything higher. Okay? So we know that 1 is one of our zeros. Okay? So x minus 1 is a factor. This guy is now x cubed minus x squared plus 4x minus 4. What do we do next? We could try the other ones. Okay? Or we can recognize that this is something that we could factor by grouping. Does everybody remember how to factor by grouping? Kind of split it in half and see if they have anything in common. Find the greatest common factors. Anyone want to see that? Review that? So you can keep on with synthetic, but let's just split this in half and see what do these two have in common? X squared. So if we factor the x squared out, we have, what do these two have in common? So x minus 1. Is that a good thing? Yes, because these are the same thing, right? So we can put an x minus 1 here. And what do we have left? Good, because we pulled a positive 4 out, right? So x squared plus 4. So this is x squared plus 4. So when the 4 goes to the other side, it becomes negative 4. It's not 4i, but not 4i, but 2i, so plus or minus 2i. Okay? Everybody see that and understand that? Okay? Uh-huh. Mm-hmm. Yep. So because this guy, let me go back. How do we know that we were not going to get any negatives? So when we plug our negative x, f of the negative x in, the variations of signs or less than that by 2 is going to be the number of negative zeros. So when we didn't have any variations of signs, no zeros. If we had had 2 variations of signs, 2 negative zeros or 0, follows the same pattern because of those complex conjugates. Okay? Let me show you that upper bound thing, though. Okay, now that we know what these guys are, okay, let's see what would have happened if we had said, okay, we got 1, now let's try 2. Okay, so I'm going to remove this factoring piece of it. And let's try this with 2. So you see that it's an upper bound. But I wanted to show you, I noticed that this was going to be a factored by grouping. So let's put a 2 in here. Drop our 1. 2 times 1 plus a negative 2. 2 times 0 plus 5. 2 times 5 plus a negative 8. And 2 times 2 plus 4. You see how we have no changes of signs? So there's no way that 4 is going to be a 0 either. Once we know this isn't happening and this isn't happening, then we'd have to go back and try 1 again. Okay? That's an upper bound. It said when I put 2 into x squared minus 2x cubed plus 5x squared minus 8x plus 4, I get 8 out. That's our remainder theorem, and that's a very powerful theorem, and I don't think we use it enough in general. I didn't make that connection until a few years ago. Okay? Yes, sir. Yep. We had 1 and plus or minus 2i. So 1 is a multiplicity of 2. Doesn't mean they're going to be unique, but we knew that we could have 2 positive or 4 positive zeros. We got our 2 positive zeros is just 1 repeating twice. Okay? All right. Assignment. Again, not many problems, because these can be tedious. You might get lucky and find a 0 right away, but we've just given you more tools for your arsenal to make this easier. Mm-hmm. Yep, the power of the first. Yep. Give me 1 second. Let me close out my recording here.